So let's start with a bit of introduction about the topic for whom of you doesn't know what a liner is. So if you see, so this is a conventional engine, the one that you usually fly with when you take a conventional aircraft, mid to large size. And what's happening today is that the engine shape is a bit changing. So we are moving from the what is called the high bypass ratio engine to something that is called ultra bypass ratio engine. Because it pollutes less, and also the noise associated with this engine is lower. What you can see here is that the engine is becoming larger in diameter. So this has an advantage. The exit velocity of the flow is less, so the noise associated with the jet is less. But at the same time, what's happening? The fan size is increasing. So what is changing is the fact that now the fan noise starts to dominate because we are reducing the jet noise, but moves also to lower frequencies because we have a lower rotational speed. Similarly, the distance between the engine, as you can see, is getting also shorter. And the distance between the rotor and the stator is decreasing. And then there is more interaction between the wake of the rotor and the stator. And then we have another source of noise, which is broadband. So in this transition, so what was the tool that we used to reduce noise? It's a liner. The liner, if you face an engine, you see a perforated plate at the inlet. That's a liner. A liner is nothing else than a honeycomb structure with on top a face sheet, which is perforated. Then you can decide the thickness of the face sheet, the sides of the honeycomb structure, and you define what is the frequency range at which the liner works. But since we are changing the shape of the engine and we are moving the noise source to lower frequencies and increasing also the band in which noise sources are relevant, then what happens is that if we keep using the conventional liner, like the one that you see on the top left, this liner to face low frequency, what should do is has to become larger, thicker. But we have an engine that is already quite large. So we are going to increase also the drag associated with the engine, which is not good. So what we want to design is a liner that is able to work both in the low frequency range, but is also able not to work at one single frequency, like the conventional liner does, but also to work in a wide frequency range. For this reason, we need to design new concept. And then we want to move from the conventional liner to something that is a bit more exotic, like a meta liner. Okay, which is a mix between conventional liners and porous surfaces. Of course, we need to keep in mind that if we expose a surface like the one on the right, then also the aerodynamic drag increases, and this is not good. So we cannot simply take a porous material and put it in the flow. But before moving to a new liner, the question is, do we know everything about the conventional liner, how it works? Let's start from the quantity that we use to measure the characteristic of a liner. This quantity is called impedance. It is defined in the frequency domain. It's the ratio between the acoustic pressure and the acoustic velocity normal to the surface. And it's an imaginary number. It has a real part that we name resistance and an imaginary part that we name reactance. The first one is more associated to the capability of dissipating acoustic energy. The second one is more related to, gives indication about the frequency of resonance and gives information about the phase. How do we measure impedance? So we want a quantity that is representative of the liner independently on the acoustic field that is on top. So what we do is we use a kind of wind tunnel. So we have the liner on the bottom, like you can see here in the figure. Then we have flow, for example, in this case from the left to the right. We have acoustic sources. These acoustic sources can be placed both on the left and move in the same direction as the flow, or ideally, like it could be in an experiment, can be placed on the right and move in direction opposite to the flow. However, what happens is that if we take a conventional liner, in its definition, the impedance that we measure shall be independent on the acoustic field on top. So if the acoustic wave travels in the same direction as the mean flow or travels in direction opposite to the mean flow, there should be no difference. This is the definition of the liner we work with. But if we perform the experiment, we see that there is a difference. So there is a difference both in terms of resistance and also in terms of reactance. So this goes against the definition of a conventional liner or single degree of freedom liner as we mentioned. It goes a bit also against the definition of impedance itself, because the impedance should be a quantity that simply represents a geometry and shall not change if the acoustic field changes. This has been found by many groups all around the world, and the reason, and this is the scientific reason behind the project, is that we think is the reason for this mismatch is that in the definition of impedance or in the measurement techniques we use to obtain and to measure the impedance, we are not considering the flow. So the flow is only a thin layer where there is refraction so a change of direction of the acoustic field, but not really an effect of the flow on the acoustics characteristics of the surface itself. Then the idea behind the project is actually to characterize how the flow behaves in terms of acoustic source, how it alters the properties of my acoustic surface, and then to define new boundary conditions that can be used to measure at the best the impedance. What has been done till today? People tried a bit of everything. First thing, let's assume that the boundary layer is really a surface through which I have a change there is viscosity effect. But this was not enough to match the impedance measured in the two conditions, with the acoustic source in the same direction and direction opposite to the mean flow. NASA people said, yeah, it might be that when we pump acoustic energy on one side, there is a slightly change of the mean Mach number into my channel flow, and then this can cause the mismatch. So they found that if I change a bit the Mach number, then there is a difference. And this difference can be such that the two induced impedance, they are the same. Someone else says, okay, Oregon says, I know that impedance shall be the same. So I introduce another quantity, beta, in the equation, such to force the impedance to be the same. They linked beta to some properties of the boundary layer, but what they found is that when I find the beta that actually is such that the two impedances match, what happens is that my beta gives me a value of the boundary layer thickness that is negative. So this is unphysical. So beta reaches the target of having the two impedances to match, but does not have any physical reason, any physical interpretation. So this is still an open question, and for this reason we decide to design an experiment and some simulations that can help understanding what's happening in the flow. The first thing we did is to define a liner. So a liner that can be tested in many facilities. The liner we designed, it's a very academic liner. It's very simple, squared cavities with orifices placed in locations we can reproduce easily numerically, and is built such that we can test the same liner in two facilities, like the one at NASA and one in Brazil, simply by changing the number of cells, but without really changing the geometries. So it's exactly the same geometry, we can 3D print it, we can manufacture it in another way, but for sure we can test in two facilities. Then when we designed the liner, we asked the company Protolab, okay, wait for the order to be placed by the two institutions, and please use the same machine and print the two liners one after the others. So this is the best we could do to be sure that the same machine was used more or less in the same day, and then what was coming out was more or less similar. Then we defined a test matrix, and this test matrix was tested in the two facilities I mentioned there. However, after about 1 year of unsuccessful numerical simulations, we decided to look at what was actually built. And it came out that the geometry we wished to have was very different than the one that we actually tested. This caused large mismatches between numerical simulations and experiments, and then we took the scan of about 50 different orifices over different cavities. And we did this work both using the sample that was tested at NASA and the sample that was tested in Brazil. And we decided to design a new liner that was representative of the average orifice we found in the experimental one. We are now today printing not printing, but building the original one as we wished with other techniques. But then at this stage, we decided to move in this direction. And what you can see is that differently from the one before, this liner has some rounded edges. So it's not sharp anymore as we designed. This has a large effect that we saw in another study that I'm not showing here for the sake of time. And then we took this new liner, ideal average liner, and we used this liner in the numerical simulations. Of course, in the numerical simulations, since I'm going to perform a spatial developing boundary layer simulation, I cannot place either 33, either 44 cavities, it's simply too expensive. Then we took only 11 cavities. The choice of the 11 cavities was based on some experimental results to say, okay, I have enough acoustic dampening to be sure that I can apply the same techniques I use in the experiment to obtain a measurement of the impedance. However, back in time, we didn't consider much the aerodynamic effects like you are going to see later, so we need to run simulations on a longer liner to have a better understanding. So, from the experimental side and also from the numerical side, let's characterize the liner. So we performed two experiments, as I said before, on the same liner. The one in Brazil uses all the microphones that you see here on the top. The one upstream, this is the liner, the one on the bottom. The one upstream and the one downstream, they are used to measure the impedance using a technique that is called mode matching. What I do is that I apply a minimization problem between a numerical solution or a simplified solution and what I measure in terms of modes upstream and downstream of the liner. I assume with a boundary condition an impedance here, and I find the impedance that best matches the experimental results. Otherwise, I can use the microphones in front of the liner, and then I do a decomposition in axial wave number of the field, and in that case, I see how the axial wave number changes, and I obtain another measurement of the impedance, such that I can compare. At the same time, I can also instrument my cavity and put two pressure probes, one at the back plate and one on the face sheet, and have a local measurement of what's happening at the acoustic source. This was done synchronously in Brazil. At NASA, we had only microphones upstream and downstream, in front of the liner, and then we used a similar technique as what we call it PRONI, that is called CHA in the NASA facility. Then we exchanged data such to be sure that also the processing technique was not affecting the results. Then we build up the numerical setup, and the numerical setup was built such to inject at the least an acoustic wave with 15 wavelengths. So the acoustic wave is not added as a boundary condition at the inlet, and the reason is that in order to avoid reflections at the boundary of my domains, I must use on both boundaries of my domains some numerical sponges. Else, I arrive at the end of my domain, I see a discontinuity in pressure, is a compressible solver, the acoustic source comes back and this corrupts my measurements. It's not as in the experiment. So we decide to add the acoustic wave in space and then to let it propagate. The acoustic, we use a lattice Boltzmann solver. The first reason is that it's compressible. Then having a Cartesian grid, it's easy to mesh complex geometries like the orifices we showed before, and we took a subset of conditions because at the beginning it took very long to run simulations. Today we learned the strategy to reduce of about 2/3 the computational time of these simulations. Of course, as you will see later, we performed a grid resolution study to be sure that the results were grid independent. Then we can start with the analysis of the experimental results. The goal of the experimental results was twice. We had two goals. The first one, we wanted to see if we saw consistent results between the two facilities. And then we wanted to build up the experimental database to validate the numerical simulations. So, the first thing we noticed when we started comparing the results in the two facilities is that we were able to match the maximum Mach number, or at the center of the cavity. We were able to match the mean Mach number, let's say in the one normal directions, but the two channel flows were built into, the two channels were different in terms of size. Then what came out is that if we match the Mach number, the center line, all the bulk, so the average, still some properties of the boundary layer close to the surface are different. In particular, we focused on delta star. And we saw that there was about a factor of about 2 between the two delta star. This is important because, as I said before, in this field, people looked at the problem mainly from an acoustic perspective. So they assumed that the boundary layer is always a thin layer, and they didn't care much about the values of delta star and then the characteristics of the flow close to the surface. The first experiment we performed was without flow. So without flow, two experiments in two different facilities using different techniques to measure impedance, they give us more or less the same results. And this is good. This is also good because it means that the two liners that were tested in two facilities have a similar geometry, which, given what we saw afterwards, was not granted. Both resistance on the left and reactance on the right, they have similar results. Of course, I'm not showing here, without flow it doesn't matter if the acoustic wave comes from one direction or the other, then the results are the same. Then we introduce the flow. In blue, you find the results that were collected at NASA, in red, the results that were collected in Brazil. This was a bit surprising at the beginning, there is quite a mismatch. So we are looking for a quantity that shall be independent on what is happening on top of it, shall be dependent only on the geometrical features of the liner, but still we measure two different values. So a bit the meaning of the quantity impedance is lost. Then we found a model that is from the 80 and comes from NLR in the Netherlands, which, using a lot of data as some empirical collection, we introduced delta star and we found out that actually the results, the expected results and the model and the experiments gave similar results. This was an interesting finding. Then we moved the acoustic source on the right side and we found two different things. First of all, there is higher sensitivity on the model we are using because there is a scatter between the results. The scatter between NASA and the Brazilian facility is more or less consistent. We move away from the expected results from the models. And if you compare the right with the left, you see actually that there is a difference in impedance between what we measure when the acoustic source moves in the same direction, propagates in the same direction as the mean flow, and in direction opposite to the mean flow. So this confirms from one side what we found out, add another variable that is the impact of delta star on this phenomena, and add other considerations another consideration is that, okay, when we have the acoustic source in direction opposite to the mean flow, also the scatter between the different techniques is larger. So what are we really comparing? That's the basic question. And this is important because there is, in the framework of the AAA, a kind of contest where people test the same liner and they tend to compare the results between techniques, but they never consider what's happening in their facility. So consider that NASA had the characterization of the flow, but barely used it. The Brazilian people didn't have the characterization of the flow before this experiment. So this is important because we are adding a new variable in order to compare results between different facilities. The difference is a bit less visible between techniques and facilities as before in terms of reactance, because it mainly depends on the height of the cavity. But if you compare left and right, there is a bit of a shift as well. So also the reactance is behaving differently. So I'm not showing here for sake of time, but what we found is that we performed, this comparison was performed by comparing the Mach number, the maximum Mach number. Then we decided to perform another experiment to compare the min Mach number, and the results were extremely consistent. Then we decided to exchange data between the two institutions. Each of us was applying his own technique, and still we found out that the technique we use, they keep, given the dataset, the results are still consistent. And then one of the main conclusions is that, okay, we need to look at the flow. These results and more extended results are now under review in a paper in AAA journal. Then we moved, in parallel, we performed the numerical results. We started a bit later because at the beginning we aimed at simulating the first liner I showed, and the results were completely different. Then on the new geometry, as you can see, the results are more consistent. As a good practice, the first thing we did is to assess the grid convergence study and to compare with experimental results. So here I'm replicating the flow conditions in Brazil, because there we have easier access and we can perform the measurements when we like. And what we find out is that, okay, the results are more or less grid independent for the second grid, the one of 40 voxel per millimeter, the one that I call it medium. And we didn't have RMS fluctuations from the experiments in Brazil, so we went to the literature, we looked at some results with a Reynolds number that was comparable with the one that we had in the facility we tested, and we found out, also using some analytical models, that the peak in fluctuations is one that we expect both in terms of amplitude and location. So we are happy enough with the simulations of the flow, so we can move to acoustics. Here I'm showing you a classical grid convergence study. For computational reasons, we decided to stay with this grid because it was enough, and also the computational time is way lower. So differently from the experiments, the first thing that we can do is to map the surface of the liner. Let's imagine that we have thousands of microphones on the surface, so we can measure locally the effect of the acoustics. We use what I mentioned at the beginning, the Dean's method, the one that samples, let's say, acoustics both on the surface and at the backplate. And here we report three different results. First of all, we start without flow, Mach 0. The acoustic wave travels from the left on the top, then we have the flow on the middle and the bottom. Then acoustic wave propagates from the left to the right, on the second one, from the right to the left on the third row. I'm selecting only one frequency, which is 1400 Hz. The reason is that this is the resonance frequency for the liner without flow. And also I'm showing only one amplitude of the acoustic of the acoustic source, which is 145 dB. In the figure, I'm plotting only variation with respect to the mean. The mean is computing on the entire surface, and these are reported on the right. And this slide shows resistance. Let's start without flow, top row. What you can see is that when I move from the left to the right, in average, my resistance decreases. This is expected because the liner is actually working, is reducing the amplitude of the acoustic source, and then I'm moving from a nonlinear regime, that is the one characteristic of 145 dB, to way less, way lower acoustic amplitude, and then I move towards the linear regime. So this is nothing wrong, but already if I start looking at a single cell, I see that moving from the left to the right of each cell, my number is changing a lot. Why? Because a bit the hypothesis behind this technique fail. I shall stay as close as possible to the orifice, because there I can assume that there is a linear propagation of the acoustic source. So no flow case, everything makes sense. I add the flow. I see less reduction of the mean value. And this is already good. This is expected because the flow reduces the capability of the liner to reduce acoustics. So the decay of the pressure source is less. But what I see is that when I move from the left to the right of each cell, the scatter changes a lot. We are talking about of a factor 4. But even more interesting is that if I stay very close to an orifice, depending on the fact that I stay on the left or on the right of an orifice, I'm measuring a different quantity. And this is something that experimentally was never observed. We redid the experiment, just placing my microphone here and here, and we found out that the same delta were present also in the experiment. So this for us is a first guideline saying, okay, take care that depending on where, if you use in situ, and this is widely done in many research centers, take care that depending on where you measure, you can get a different value. So work always in terms of delta. Things looks more or less similar if we move the acoustic source in the direction opposite. The same trends are also visible if I look at the reactance and also at the phase relation. And also in this case, what I see that if I stay close to the orifice, that's where I'm actually interested in, still, depending on where I'm measuring, I can get a different value of reactance. So in situ method provides good results, local results, but they can vary a lot depending on where you are. So then we decide to apply on the numerical database the same adduction techniques as we did in the experiments, and in particular the KT and also the mode matching. Why we use these other techniques? Because they provide more or less an average value. They assume that the surface has a uniform impedance, and then we get more or less an average value of what's happening on the surface. And here in this figure you see the comparison between the experiments and the simulations. One point to highlight is that the experiments were performed on 33 cavities, so you have more reduction of the acoustic source, so this helps a lot in performing the estimation of impedance. In the numerical simulations with 11 cavities, considering the edge effects, we were a bit borderline. But however, what we see is that in terms of order of magnitude and trends, we recover the same information. So when we move from the no flow, the black dots, towards the flow case, there is an increase of resistance and a slightly shift of reactance. This is as expected. More or less the trends in terms of comparing acoustic source in the same direction and direction opposite to the mean flow is captured. And if we look at in situ and we compare with mode matching, this is another interesting result, there is quite a difference. So in situ and mode matching, they do not provide the same results. They do provide more or less the same results if I consider the top of this error bar. And the error bar is nothing else than the maximum and the minimum value that I measure on the surface of the liner. And while the measurement point here is taken at virtually the same location as in the experiment. So this gives even more confidence. Then we can start looking at what's happening when at the flow. So within the flow, when we introduce the acoustic source. First thing, let's see what happens if I compare with a smooth channel flow. So my liner is a rough surface, so it's really changing, it's introducing drag, it's changing the flow evolution, it's changing the pressure drop, it's changing everything. The first thing we do is to compare just upstream and just downstream of the liner, of the 11 cavities, the boundary layer. So as you can see, there is quite a difference in the boundary layer. The rough surface is changing the flow, this is expected. Then we add the acoustic sources, and what we see is that when we add the acoustic sources, both at 130 dB and 145 dB, it doesn't look like that the boundary layer is changing a lot. So I see that the blue, the red, and the blue, red, and green dots, they more or less overlap. But let's go closer and let's see what happens close to the surface. So first of all, we can plot the evolution of the boundary layer. So the point where more or less the velocity reaches the 95% of the maximum velocity. I am non-dimensionalizing with respect to the smooth case upstream, at the same location upstream. And what we can see that the boundary layer changes a tiny bit because of the presence of an acoustic source. But after more or less 10 delta, which is something that has been found in many experiments, let's say we forget about the fact in this first part, we are more or less in the transition region. We still feel the fact that my surface has changed from a smooth to a rough surface. Afterwards, this is the reason why I shall go with a longer liner, because then afterwards things, I forget, let's say, this transition region. But more interesting is what's happening on the right. If I look at the delta star depends largely on the introduction of an acoustic source, because it increases. And now we are going to understand why. And in general, what I see is that when I compare with respect to a smooth wall, there is an increase of delta star. Why? And this one is also expected. Similar features were found if I look at theta or if I look at the H factor. So delta star and theta are changing. They are still within a turbulent boundary layer H, but they change in a different way because of the introduction of the acoustic source. They also change depending on the frequency of my acoustic source. With 100, and in particular, if you look at the figure here, the 1400 Hz is the one that increases the most delta star, and this is because it's the frequency closest to the resonance frequency of the liner, the one of a maximum amplification. And it also changes if I move the acoustic source from upstream to downstream. So my flow is changing because of the acoustic source. And in the techniques I use to reduce impedance, I don't consider that. So this is already one limitation of the technique I use to measure impedance. Why? So what happens close to the surface, let's start without any acoustic, is that the flow sees the cavities, wants to enter the cavity. So you create a vortex that is better seen here, and you introduce momentum into the flow. So this is somewhat known. Then let's see what happens when I introduce the acoustic source. When I introduce the acoustic source, what happens is that the flow this is delta with respect, so it's a point-by-point delta with respect to the case without acoustics. Okay, so we are seeing variations. They can be large, or let's look at the large variations with respect to the case without. And what I see here is that depending on the amplitude of the acoustic source, I am changing the flow field. So the flow is pushed to enter more or less, and in particular, I am increasing the amplitude of the velocity fluctuations because I'm adding a periodic solicitation to the flow that is moving up and down. And therefore, what is happening is that also the amplitude of the velocity fluctuations are changing. So why we saw that trend in delta star? Because I'm continuously pushing momentum with different frequencies, with different amplitude. There is a connection between the two orifices or the three orifices, depending on the plane where I am. And this is causing the flow to move up and down. And this is also causing, if you remember from the contour plot of impedance, the fact that I see peak highest, let's say the maximum and minimum values of impedance close to the surface, because I am including in the estimation of my impedance, where I shall have only acoustic information, also periodic fluctuations of hydrodynamic nature at the same frequency. So the two are strongly coupled. Furthermore, in this specific case, one interesting thing is that the rough surface is introducing an instability. So if I go a bit fast on it, but if you can see here I have the wavelength divided the length of the liner. So what I see is that either the length of the cavity, each more or less 1.5 cavities, I introduce a long wavelength instability. This has been found in many studies. It's not clear yet why, but what is important is that it doesn't depend only on the flow, but depends by the fact that I have an acoustic oscillation. So the flow is introducing also an instability at a frequency that is way lower than the frequency of the acoustic excitation. And of course, this has an effect on drag. So our goal now is to understand how to reduce drag by minimizing also the interaction between the acoustic source and the flow. The last thing I want to show you is, so the first thing we understood is that, okay, I have a vortex. This vortex is somewhat blocking the acoustics. Then it's changing a bit the shape of my original orifice. This is one of the reasons why my resistance goes up. I have a smaller orifice. But this doesn't justify at all the trends that I see in the impedance. So I want to see how much energy I'm dissipating through aerodynamic fluctuations, and for this I use the Howie corollary. But I need to know one quantity, that is the acoustic velocity. How do we extract it? There is a full study that I'm not showing here. In this case, I'm using SPOD. We are not sure it's the best, but we are using SPOD at the frequency of interest. Luckily, at this stage, we know the frequency, so I can sample the SPOD first mode that resembles the acoustic one at the frequency of interest. And what I see, this is the velocity profile in the middle of the liner. Here, the red line you see here, the middle of the orifice. And here I'm comparing the acoustic velocity without flow, so kind of very uniform acoustic velocity that goes up and down, and with flow. This confirms what we saw before. The vortex that is created is somewhat closing the orifice, to make it simple. But in the moment in which I increase the amplitude of the fluctuations, I see that also here I start having a fluctuation of this vortex. Now, how do we interpret this curve? So let's start without flow. And what I see is that what I'm interested in is this red quantity. I went fast before, but when this quantity is positive, it means that I'm dissipating energy. When it's negative, I am creating acoustic energy. So if I move to the case without flow and I plot the integral on this contour, I see that both in the inflow and the outflow cycle, I'm always dissipating energy. And this is good. So I have two cycles that dissipate energy. I have acoustic velocity everywhere, more or less, in my orifice. So this is working properly. Let's see what happens in the moment in which I introduce the flow. I am localizing the regions where actually I'm dissipating energy a bit on the shear part here and close to the downstream edge. Remember that the flow comes from the left. But in the outflow cycle that you can see here, I don't have any more a positive value. So the interaction that is happening close to the shear layer is actually not contributing, is such that I have a smaller orifice and I'm not dissipating in both cycles. So this is the reason why my liner works less. This is the reason why I dissipate less energy. This is the reason why we see that the liner is performing a bit less better than what we see in the absence of the flow. Now the big issue is to understand, and this is work in progress, where do I compute that integral? Shall I consider everywhere? So I'm introducing also the hydrodynamic part that I'm unable to separate from the acoustic one. Shall I consider only the orifice and the cavity? We are trying to understand how to use these results in order to correlate at the best what we measure in terms of the acoustic dissipation with what we see in terms of some pressure level decay. To conclude this talk, I think I was more or less in that time. The mean flow is relevant. So we cannot discard the mean flow in the adduction process. We need to know the flow and to characterize the facility in which we are testing things. For this, we are planning a simulation on let's say, a nacelle, because there the pressure gradient changes a lot and the delta star will evolve in a totally different way. The impact of the acoustic wave is extremely relevant, and it changes the flow. This is something that is not done if you use a combination of runs plus computational acoustics like linearized Navier-Stokes equations. In the case, you assume that the flow is the flow. And another thing that is very interesting is that the shape of the liner, I'm not showing here, but if I move from a sharp edge to a rounded edge like the one I showed you, this changes a lot, also the way in which delta star changes, because I have a different flow within the orifice itself. So with this, I would like to thank you for listening to me, and I'm open to every question. Thank you.
Thank you very much.
Thank you.
Okay. Questions by the audience?
Thank you, Francesco, for the presentation. I have just a simple question to warm up. For the facilities in Brazil and the one at NASA, did they do a characterization of the acoustic of the tunnel before placing the liner inside?
Yeah.
Because so the peak that we could see in damping at like about 1,400 hertz was due to the presence of the liner. Because there's in the blue, I don't remember which one is the blue one, but there was a blue outlier.
This
In the
this
damping, no, you passed the slide already. I think it was 2 or 3. Yeah, exactly. You have like a peak in the normalized resistance at 140.
This is an
1400.
issue of the measurement technique you use for reducing.
Okay.
We saw that taking the same data and using the same data and the codes from Brazil, that point doesn't appear.
Okay. And then so here you're presenting the normalized resistance that is only imputable to the liners. You already subtract the one of the tunnel.
Normalized means divided by the impedance of air.
Okay.
That's what we name as normalized.
Okay, cool. Interesting. Thank you. And if I may, what do you think if, so the flow going through the orifice is kind of a problem for the performance, right?
Mm-hmm.
Why? Would it be a solution to put a membrane there to let to just close the orifice by a membrane that would let the acoustic energy pass, but not the flow?
Yes, but you want to have the vorticity to be generated because it's the vorticity that is dissipating acoustic energy. So if you remember this figure here, the one on the left, that's what is actually dissipating acoustic energy. So you want to have this vorticity that is generated. There are some concepts that use anyhow, called more or less on the active side, where they use membranes to dissipate, eventually to create balance, but there is not much yet that I've seen in the applications work.
Okay, thank you.
Okay, Oscar, go ahead.
Thank you very much for the presentation. It was very interesting. This is a follow-up to Luca's question. When you were defining the liner, I thought that you said that the liner was made of a porous material with a perforated plate on top of it.
No, it's a perforated plate and a honeycomb structure.
And there is a cavity.
It's a cavity, yes.
Okay, so could you still have something like that if you use a porous material, right?
That's my next step. So now the issue is to, so the idea is to have a porous material somewhere, we don't know yet well, to increase the band in which the liner works. So to mix a bit, it becomes a kind of multi-degree of freedom liner. Because in other concept, this is an evolution of what we call double degree of freedom, where you have a cavity and within the cavity, you have another perforated plate, for example. In the case, you create 2 peaks of absorption. Ideally, if you add the porous material, you expect to have a broadband response. Mm-hmm. The issue, speaking with particularly with the Acoustic Research Consortium, is on the application side. So I will do it because luckily I can forget a bit the application at this stage. But is that when you are flying, then that part will become dirty, it's difficult to clean, and then performance goes down. But yeah, that's something we are thinking to go.
Okay, and then also related to that, how are you performing your simulations? The flow is turbulent, the flow is not turbulent?
The flow is fully turbulent. This I forgot to mention, sorry. We are forcing the flow with a physical trip, with a kind of zigzag trip, a certain point, such to have in my domain, in my computational domain, more or less as close as possible the same boundary layer as in the experiment at the beginning of the liner.
Okay, and then my guess is that the difference that you observe between the boundary layers in the 2 facilities has to do with the tripping of the boundary layers?
No, in the facility is simply a turbulent boundary flow, turbulent boundary layer that evolves because the Reynolds number is high. So it's due to the fact that 2 facilities are different in terms of really structure of the facility. Mm-hmm. And also the way in which let's say the first convergent is designed and so on. So and then the sides of the 2 facilities is very different. Let's say the duct sides.
Okay, thank you very much for the
Welcome.
presentation. Very interesting.
Thank you.
All right. Is there any other question? Very last? No? Then I think we can thanks again, Francesco.
Thank you. Thank you for listening.